Okay, so with GKR basically we have our IOP. We can generate our proofs. We can verify our proofs. But then those proofs are big, right? And we want to actually make the protocol succinct. We want to reduce the size of the proof. That's why we now use polynomial commitment schemes, right? So like last week we looked at KZG. Who can just give us a brief overview of what we did last week with respect to KZG? Just a brief high level stuff. KZG. Oh, you don't need to.
KZG is a development scheme where the program commitment and the full size constant.
Right, the commitment to the polynomial
Yes, commitment to the program.
and the proof size are constant size.
The other where as the commitment increases, the proof size also increases. Right. Then also I think one thing we talked about KCG was how like they do the powers of tau and how they also use the addition commitment, which is the jury or something for the electric code. So the fact that you don't need like the goal is to hide tau and then people can like you can compute the evaluation of the polynomial without actually knowing the value that you're evaluating as using the justification where you have like the powers of tau and then you have the polynomial in like the coefficient form or whatever form you're using it like to get the evaluation even though you don't still know the value that you're evaluating the polynomial at. And then I think you talk about G1, G2. Then we spoke about many things here. Well, let me just say this last one. So where you have Q of tau being the proof. So a prover is going to like evaluate the polynomial. As like let's say the verifier tells the prover, okay, I want you to evaluate this polynomial as a, even though the verifier does not know the polynomial, but the prover knows the polynomial. So the prover makes a commitment to the polynomial and gets a commitment, then sends it to the verifier. Then the prover, who doesn't have idea of what the polynomial is, tells
The verifier.
the verifier who doesn't have idea of what the polynomial is, tells the prover to open the polynomial at some point. And then the prover also does that by getting the value of f at a and sends it to the verifier. So using that formula I wrote down, the verifier can actually attest that the prover opened the polynomial at that point. That's one. And the verifier can also attest that based on the commitment that the prover sent it, we can tell that it was that exact polynomial that was opened. And that's
Okay.
Okay.
Yes.
In summary, KCG is divided into two. The first part we talk about trusted ceremonies. So here we have our encryption, like our G, like homomorphism, homomorphic encryption, because we want to encrypt our polynomial using homomorphic. So the second part is the commitment. Commitment using partial whatever we call it. Then
Pedacin.
Pedersen commitment, right? So then the fourth part is where the program verifier goes there. So process of ceremony, Pedersen commitment, then the program verifier.
Okay. So with respect to that Pedersen commitment, like the actual Pedersen commitment, there's more to it. It's not just G to the power. Yes. But I just like said it because that's kind of like an easy way to just think about it. So I just encrypting those values, not that we're actually doing a Pedersen commitment. Yeah. Because Pedersen commitment, we also need to like include some hiding property and stuff. Like there's actually more to it than just encrypting those values. Okay, so last week we looked at how we can use a or how we can commit to a univariate polynomial, right, using KZG. And one of the major things that made it possible was because of the fact that we could separate our coefficients from the powers of tau, right? If we're not able to do that separation, then it would have been a problem, right? We separate our coefficients, we have our coefficients, we have our powers of tau, and when we want to evaluate, we actually now do the dot product of the both of them, right? Multiply them element-wise and sum it up. So this week we are going to be looking at multilinear KZG, right? Multilinear KZG, and this is actually what you're going to be using to make your GKR succinct, right? So for those of us who want to implement the normal KZG, you can, right? But everybody must implement multilinear KZG because you need multilinear KZG to make your GKR succinct.
So what does it mean for GKR?
Okay, so currently, when you perform the GKR, when you have a circuit and you want to prove that you executed the circuit correctly, we generate a proof, right? Which basically comprises of the sum check proofs for each layer, right? But that proof is big per se, right? Especially, let's say the input to the circuit. The input to the circuit, if the circuit is a very big circuit, the input to the circuit can be up to 2 to the power of 20 field elements, right? Which is very big. And we don't want the verifier to actually have to keep track of that very large input. You get? So we want to be able to reduce the size of that input to just one field element, but then the verifier will still be able to like verify that the circuit was actually executed correctly. So making it succinct is basically reducing the size of, for now, what we're majorly going to be focused on is reducing the size of the inputs. Does that make sense? Yeah. So we're going to be looking at multilinear KZG, and what is multilinear KZG? It's just a protocol to enable us to commit to a multilinear polynomial. A multilinear polynomial has more than one variable, right? And we want to be able to commit to that polynomial. In the univariate case, right? When we had a univariate polynomial, let's say x squared plus 3x plus 2. The way we could commit to this was by evaluating it at tau, right? So to commit to the univariate, we evaluate it at tau, right? So we just plug in tau here, so it becomes tau squared plus 3 tau plus 2, right? And whatsoever thing we get is our commitment. Did Dr. Wright, did this make sense? This makes sense, right? So we just evaluate this polynomial at tau, right? But now when we're talking of multilinear, let's say we have a polynomial. Which polynomial should we? Who should give us a polynomial? No, a multilinear poly.
3ab plus 3 plus 3bc.
2ab,
3bc.
2ab plus 3bc. Can I? Okay. Okay, so we have a multilinear polynomial now. It has more than one variable. How can we commit to this? Does anybody want to make an attempt? Two different powers of tau. But none of this actually is of a higher degree, right? All the variables are of degree 1. Okay, we get tau for each variable. Okay. Nice. Okay, so after getting tau for each variable, we evaluate the polynomial at the taus, right? Okay. Yeah, full evaluation, not partial. Because our commitment, we want our commitment to be a single field element, right? So, okay, so we get tau for each variable and evaluate the polynomial at all the taus. Okay, at all of them. Okay, so can we do an example?
Yeah.
Okay. So let's say this is our polynomial, we want to commit to it. There are 3 variables, right? We have A, B, C, right? So we want to commit to this polynomial. How do we do that? We pick tau of A. What should we use as tau of A? 5. Tau of B? 2. Tau of C? 4. Okay. Nice. Okay, so we want to commit to this polynomial now, right? What do? We evaluate the polynomial at the, our values for tau. So we have 2 to the 5, right? So the 2 plus 3 to the to the 2 to the what? 17. So this is 20, right? 5 times 2, 10 times 2, 20 plus 17 times 6. That's 17 times 6. 102.
So you're going to like do like 3 trusted setups for this house to get the house.
No. But we're going to talk about the actually Multilinear KZG. Actually, like the trusted setup for Multilinear KZG, that's true. That's crazy. It's not crazy that it's hard, but it's actually I and Wizard were trying to figure it out. So what we did was just like generate what we will use, but actually the trusted setup that people can contribute to, it's not so straightforward. Yeah, and that's true. That was an uncompleted. That was an uncompleted research. Okay, but let's just continue for now. Okay. Well, we're going to get there. You're going to see what we saw, right? When we're figuring it out. So this is what 122. So this 122 is our commitment, right? You can think of it as our commitment to this polynomial 2ab plus 3bc. We pick different values of we pick different random values for the different variables, and then we do what? We evaluate the polynomial at those random values. So basically it's just like normal evaluation of a polynomial, right? And we have our commitment. Okay. This makes sense, right? Just pick random values for each variable and then evaluate the polynomial at those random values. Makes sense, right? Similar to the univariate case where we picked a random value for tau and then we evaluated the polynomial at that random value and we got the commitment. But now this is not so straightforward, right? Because when we actually want to commit to the polynomial, our multilinear polynomial, we're working in evaluation form, right? We're working in evaluation form, and we are also working with an array, right? An array of the polynomial in evaluation form, right? So if we want to go about this programmatically, how can we go about it? Does anybody want to attempt?
How do we go about it? Is it doing what exactly?
Like, in the univariate case, we had the polynomial and I wanted to commit to it. So we sample a random tau and evaluate the polynomial at that random tau, right? Then when we wanted to now think about it programmatically, that was where we now had to start thinking of, okay, how can we actually separate? We want our taus to be random, right? We don't want anybody to know our tau. So that was what now prompted us to do the separation, where we have the coefficients and the powers of tau, right? so that we could now do like a dot product of them, of the coefficients and the powers of tau, right? So that was when we now wanted to think about it like programmatically. How can we go about implementing this? So in this case now, in the case of the multilinear KZG, okay, we know, right, that to commit to the multilinear polynomial, all we need to do is sample random taus for each variable, right? And then we evaluate the polynomial at those random values we sampled to get our commitment, right?
So now we want to find a way to hide the while still evaluating this.
While still evaluating, exactly.
I think since we really, I think basically what we can do is we'll have to like repeat the invariant process multiple times for the variable.
Okay, so would that be in the commitment? Like we need to repeat the univariate.
You know, the invariant, what we did in the invariant was just for one variable. Right?
Yeah.
So our 50, since we have multiple variables, so we can repeat the same process for
all of them.
For all of them. So basically, we can maybe like skip A and hide, like evaluate the other variables. Then when we skip and evaluate the other variables, now we have only A as the active variable. Then we do it for that one. Then we do the same thing for B and the same thing for C. That way we can do it for all the variables. That works.
Okay. Well, if we do it that way, then you know that means we'll need to be working with the powers of tau for each of those variables.
That's what I was thinking.
But then when we want to evaluate the polynomial, we're not actually evaluating it at the powers of tau. So that's like for A now,
Yeah.
let's say in the 2ab plus 3bc, right? If we generate the powers of tau for A, that will be say a to the 0, a to the 1, right, a to the 2 and so on. If we evaluate this, or if we do like, because you know this is our polynomial, we're basically working with it in the evaluation form, right? So if I got you right, what you're trying to say is that we should get A up to the number of, let's say if this is 0 and this is 10, we're going to get A not to the,
I think that would be the accuracy of repeating it for the two variables.
will be crazy, right? To be crazy. And it won't even be correct. Yeah. It won't even be correct. Actually, let me not stress the people too much.
What is
Okay.
where A is 0, where is 1?
Where A is 0. Wait, oh, is it this side?
Yeah, maybe we
Okay.
can
Yeah, actually,
maybe
yeah.
where A is 1.
Okay.
And since we know that is where the tau value will be.
So A is 1, right? So let's say 0, 0, 0, 1, or 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So where A is 1, so that is this point, right? Those 4 points. Okay. So what are we going to do?
Maybe we can now multiply by it. So I'm thinking my follow that.
Yeah, actually you have an idea and it's good. You're there to say something.
Yeah, and when we evaluated the polynomials, like we were doing has it been used now? Like we never talked about points or energy stuff.
Yeah,
Is this
you know,
different?
no, we're still going to do it that way, but like basically anything we can do in the clear, we can also do encrypted, right? Or the encrypted values. So I don't want to complicate it for it. I just want people to understand it in the clear first. Then when you understand it in the clear, it will be easy to relate it to the encrypted values. You get just like how we did for the univariate case, right? But everything is still going to be happening in the encrypted values. It's okay. Bilikis, seems you wanted to say so. Okay, so let's take out this guy. This guy is close. Okay, so there's one thing, right? And that thing is that when we wanted to evaluate or when we wanted to commit to the polynomial, we picked random values for each variable, right? And then we fully evaluated. What is a full evaluation of a multilinear poly?
A series of partial evaluations.
It's a series of partial evaluation, right? And thinking of it in the evaluation form, for each partial evaluation, we are reducing the size of this array by half, right? So if we have a polynomial in 3 variables, after we partially evaluate at the first variable, we are going to have a new polynomial in the remaining variables, right? So that first variable will go off, right? Then we'll have a new polynomial in the remaining variables, right? Is everybody with me? And then when we partially evaluate that one again, we have a new polynomial in the remaining variables, right? Right?
Yeah.
I will just continue like that until we have a univariate polynomial, right? Where we'll now evaluate at the last variable. Does it make sense? Makes sense, right? Sure.
How is it?
Okay. So we have the polynomial, let's say 2ab plus 3bc, right? And we said let our tau of a be what did we use? Yeah, let me just copy it. Right? So this polynomial is actually in evaluation form. We have like 2 to the it actually has 3 variables, right? 3, right? So in evaluation form, the number of evaluation points will be, let's say, an array of 2 to the 3 elements, right? And we said when you want to commit to a polynomial, you pick random values for the different variables, right? And then you evaluate that polynomial at those random values. What is full evaluation? Full evaluation is just multiple partial evaluations, right? So first of all, we have this polynomial with 2 to the 3 number of evaluation points, right? And then when we want to partially evaluate it at tau of a, we partially evaluate it and we get a new polynomial in BC, right? So okay, so partial eval at tau of a equal to 5, so that's 5b plus 3bc, right? Which is 10b plus 3bc, right? So this polynomial has how many number of variables does it have? Okay. 2, and then eval point. Eval point is 2 to the 2, which is 4, right? Right? Okay. So we've partially evaluated at A. This is our new polynomial, right? And with this new polynomial, we want to partially evaluate at B again, right? Because the idea is full evaluation. Full evaluation is consecutive partial evaluations. We partially evaluated at A, right? So the next thing now is to partially evaluate at B, right? So partial eval at tau of B equal to 2, right? Okay. So this is the polynomial we are working with now, right? Because we partially evaluated it at A. We had the initial polynomial. We partially evaluated it at A. We had a new polynomial. We're still working with that new polynomial, right? We're going to now partially evaluate it at B. So this will be 10, 2, right? Plus 3, 2C, which will give us 20 plus 6C, right? So this 20 plus 6C now, how many variables does it have? 1, right? And how many evaluation points? 2, right? So this is basically a univariate polynomial now, right? And then we're now going to partially fully evaluate. We're going to fully evaluate this polynomial at. That's because it's the last one. Yes. So we're going to fully evaluate it at tau of C. Tau of C, which is 17, right? So that will be 20 plus 6 to the 17, right? Which was 122, right? Right? And this is now our commitment. Does it make sense? Okay, so we get our 122, which is our commitment. So that's just like one idea, right? We know we're working with evaluation form, and we know we want to partially evaluate each variable, right? Want to partially evaluate each variable at its own tau, right? Want to partially evaluate each variable at its own tau. So when we partially evaluate, the size of the polynomial reduces. This is what we have figured out per se, right? Okay. So okay, so now the thing is, we want to be able to think of this programmatically, right? We're basically working with our evaluation points, right? We're working with our evaluation points, and basically, if we want to evaluate a multilinear polynomial at a point, but then we want to do it in a way that we can actually do a dot product, right? Are we understanding? Okay. In the univariate case, when we're thinking about it programmatically, we had the coefficients. We had the coefficients array, right? And then we had the powers of tau. And what we just do in order to evaluate the univariate polynomial, we do a dot product, right? We want to achieve something similar, right? We want to achieve something similar with the multilinear case. But in the multilinear case now, since we know this coefficient array is not actually the coefficient, right? It's the evaluations of the polynomial over the Boolean hypercube, right? Right? And we need another array
So basically, sir, we are looking for another array to multiply that polynomial
yes,
evaluation formula such that it partially evaluates that polynomial.
it's fully evaluates the polynomial or partially evaluates.
How are we going to do that? Maybe we can just use it to work with the partial evaluation, like how do you do it? How do you
Okay, so if we wanted to go this way, we went, right? That means we will know tau, right? You get? So if we wanted to go this way, that means we will know tau. Like we will know the tau for each variable. But we don't want anybody to know the tau for each variable, right? Because because anybody that knows it will basically be able to generate a false proof. You can remember how a prover that knew tau generated a proof that the verifier accepted last week in the univariate case. Can we remember?
Yes.
Sure? Okay. So if we want to actually go this route, that means we will need to work with tau in the claim, right? So that's why we can't actually do this.
So I was thinking about something. So that's the second array now.
Yeah.
Since like what you explain now and what I said, that means if is it possible that we can maybe for that array, I know we're going to have like powers of tau.
This
But
second
this is-
array, right?
Yes, it's not going to be exactly like the univariate, but it's still going to be that G's or something. So maybe those places, maybe like since one represents like a bit on, maybe that will now tell what power on G, like what variable on G will be there. So maybe if it's like maybe the third bit that is on, we now know that okay, this is C that is there, like G to the C. Or if it's like 0, 1, 1, that means the G is going to have both B and C. But like that's how I was just thinking.
Okay.
Maybe G raised power, yeah, the way these three bits are like A, B, C.
Where is A, B, C? Like that's basically, let's say, the last person in this array, right?
Yes. So for like each of them, each of the like bit representation, you're going to have like G to be something.
Okay. So for each of them, for this one, we'll have, let's say, G to the something.
Like this would be like A, maybe if I don't know it's A dot G to the B dot G, yeah, G to the C, yeah.
Something like this.
Yeah.
Okay. You're actually making some nice attempts, but you're not exactly there. And this doesn't look correct. But then, like, you're making nice attempts, right? But any other person wants to attempt. We want to get an array, right? Such that if we do a dot product between that array and the evaluations of the polynomial, we are going to get the evaluation, or say partial evaluation, of that polynomial. Okay, so let's just think about it as partial evaluation, right? So we want to get an array so that if we multiply this guy, which is the evaluations of the polynomial, at that array, we are going to be able to partially evaluate that polynomial. Does any other person want to make an attempt before we actually like look into it?
The part where like the partially evaluating around everything, I think maybe G to be raised to the power of 0 or something. Like that place should be basically 0. Since that variable is disappearing, I don't know.
Okay, so the thing now is like for now, let's not think about it with respect to G. You get? So that it doesn't complicate things. Because we know that anything we can do with declared values, we can also do with the encrypted values, right? So we just need a way to get certain values that when we do a dot product, we are going to get the evaluations of the polynomial. I think it's looking maybe to this thing. So let's reduce the problem, right? Let's focus.
Sorry, but they don't have to be the same size, right?
No, they have to be the same size. They have to be the same size.
Or for normal dot product, they don't do
For the normal dot product, no, they have to be the same size. The two arrays, right, that you want to perform the dot product on, they have to be the same size.
But like, when you're multiplying vectors, they don't have to be the same size. Then when you are multiplying,
Isn't dot product? No, they have to be
They
the
have to
same
be the
size.
same size. Just put it is IG. If it's
Yeah.
IG,
you can multiply ij by ijk now.
yeah, it's 0K in the first one.
Isn't
You can multiply ij by ijk.
Yeah, you can.
It's kind of like a matrix more now.
No, even with the dot product.
The other one will be
The other one, the value is 0.
That one will be 0 now.
Okay,
we
yeah.
still have,
But then there'll
we still
be,
have the same array.
if those ones evaluate to 0, then
It's still the same thing.
yeah. So okay, no, those ones they're just indexes for yeah. So they are just indexes. Like let's say you have two arrays where I is equal to 0, right? If you want to perform a dot product on this array, and you want to use a for loop, yes. So this is 0, 1, 2, 3, 4, 5, right? So you're just increasing I. Let's say maybe you're using I to index this array, and you're using J to index this other array. Yeah. So okay, so let's reduce the problem. Is it okay?
Yeah, sure.
So we have a polynomial 2a. 2a. In evaluation form, evaluation has 0 and 1, right?
Yeah.
So this will be 0 and 2. right? And we want to we want to fully evaluate this polynomial at a equal to 5,
Okay.
right? And we want to do that by looking for another vector we can do a dot product with this array, right? So it's not hard, right? So that would be what?
Anthony, let me
So the answer is meant to be 10. That's
Yeah, if we partially evaluate at 5, we are meant to get, which is 10, right?
at just 1
What's
point.
that?
Eh?
Oh, that's true.
Sorry, that's 2. Right?
That's meant to be just 1 point now. So the result is meant to be
Yes.
just 1 point now.
Yeah, the result is meant to be 1 point. We're supposed to get 10.
okay.
Zero and five.
Me, I don't know. I can do this with maths, but I don't know how possible it is.
Okay. Let's do it.
Since it's
What comes
since
down
it's
to 0 and 5?
since it's dot product, right?
Okay, 0 and 5, right?
Yeah, 0 and 5.
But why is 0 and 5?
Because if you see R at the end,
Like, why you're saying it is because you're seeing it, right? Good.
so the value that you're evaluating is like 0, 1. The indexes are like 0, 1. Then the tau value that you're evaluating at is 5. So that's
Yeah.
like saying tau is 1, 0, then tau is 1, 1. It's a second array.
Tau to the 0, tau to the 1.
Oh, that's 0.
So
And then there's 1. No, but even if instead of 0, that can also be 1, right?
Eh?
Instead of 0, 5, that can also be 1, 5.
It's because
Yeah, it's because this one is 0, right? So even 1 million and 5 will still work.
so
Right. So, but
what is important to have abstract is
When you like in evaluate, we don't have 0, we have like natural.
where we don't have 0, right? Plus 5. So this will be 5, right?
accept
And 7. And this will be 15.
it's still 0 and 5.
Is it 0 and 5?
No.
Let's say 0 and 5, right? So this will be 0 plus 7 times 5, which is 35.
Oh, wow.
Okay, so that's the problem. We're reducing the problem to the most basic of problems, right? Okay.
When 7 is raised to the power of 1, and 5 is raised to the power of 0, yes, sorry, it's 7 times 2. Sorry, what's 7 is power? This 7 is multiplied by 2.
Where is the 2 coming from? Where is the 2 coming from? Where is the 2 coming from? Okay, let me give you people a hint. Should I?
Yeah.
What is check 0?
1 minus
1
X.
minus X.
1 minus x. Check 0. And what is check 1?
X.
Can this guy be useful in any way possible?
Mention it, yes.
Obviously.
I think so.
Okay. How?
So that would basically
Because
be
in
the
a
second one.
Hmm?
so
How?
in a way, yeah.
Continue.
Yeah.
Sorry, Lena.
Okay, like what I'm thinking is that based on the Zealand and vacuum, right? So you will use the what's it called? Check zero for places where the A value is zero and like I vacuum.
Okay.
And then
So, sorry. Basically, what you're trying to say is that we have 5, we have 7, right? And then we're doing a dot product with check
zero.
and check.
Yeah, when the x is at the value you want to evaluate at 10. No.
Interesting. Okay.
I think so.
Does it work?
Yeah.
Which you wanted to say?
5 minus 6 minus 20.
Yeah, it was like almost
Okay, similar, right? So let's actually expand this, right? Let's expand this. So this is 5 1 minus x, right? Plus 7x, right? So this is 5 minus 5x plus 7x, which is what?
5 plus 2 is
5 plus 2x.
Everything 5 as x.
Where x is 5, we have is it the same?
yeah. Actually, I did it too, but I used a normal dot through A and B. Like I converted that to a vector. I did 5I plus 7G multiplied by dot product of AI plus BG is equal to 50. So I think I got 5A plus 7B is equal to 50. I never knew, so I was now trying to look for the relationship between A and B.
It's a and B.
So now you give us that at evaluation at 0 and evaluation at 1.
Okay. Nice. So, okay, so in this case, what would this array now be? This is 5, this is 7, right? If we want to partially evaluate that x equal to 5, this would be 1 minus 5, and this would be 5, right? So which is basically 5, 7, 4,
No, my
sorry, minus 4 comma 5. Eh? Sorry, eh? It's not making sense. Bilikis. Okay. Okay, so this minus 4, right? So now, right, we've been able to separate. We have the evaluation form, right? And then we have something like an array that we can actually use to evaluate the polynomial, right? And this array is totally dependent on the points that we want to actually evaluate the polynomial at, right? Like this array is totally dependent on the points we want to evaluate the polynomial at, right? Are we sure?
Yeah.
Okay. So that was for one variable, right? Let's take it back up. Let's bump it up.
So this work for all possible any possible number.
For any, like this one, yeah. Because this is x, right? X can be anything. That's the beauty of abstract algebra. So x can be anything, right? So if we have a univariate polynomial, basically with degree 1, right? A univariate polynomial where the degree of the polynomial is 1, this will work, right? But if the degree is more than 1, then we need, for univariate polynomial, right? If the degree is more than 1, then we need the powers of tau, right? Okay, so this is a univariate polynomial in evaluation form. But in the powers of tau settings, we're working with the univariate polynomial in coefficient form. Right? So I'm sure some of you can come up with committing to a univariate polynomial in evaluation form using something like this.
So that for every thousand, you have to like take 0 and take 0.
For every tau.
Like 4 minus tau A. 5 and 7.
So, okay, yes. Like this array, right?
Yeah. Then so for each tau A, that's the limit.
So, I think we're getting to, we're not really going to look into the trusted setup today, right? But we're going to see the problems associated with the trusted setup. We are going to look at it, and maybe we'll be able to even figure it out in class. As all of us are here, right?
The problem is in process
Of multilinear polynomial.
research
Huh? Actually, like, there is no, I won't say there is no, but I've not seen any implementation of trusted setup for multilinear.
So but you figure it out.
We'll figure it out.
Then we have to
We'll
figure
figure
it
it
out.
out. No, there may be, but maybe I've not checked enough, right? So it's possible that I've not checked enough, but I've not seen. You get it. It doesn't mean that it's not out there. It may be out there, right? Or maybe I've not checked enough to see it. You get it. Okay. So does this make sense? This makes sense, right? Let's now do for 2 variables. Is that okay? So which polynomial should we use? Let's use our normal guy, right? So let's say 2a plus 3b, right? Plus 2. That plus 2 there is just so that we won't have zeros and some people will be looking for how to
I like the situations where we don't have the constant. I like the situations where we don't have the constant.
no, it will still work. I'm just putting the constant there so that we don't have a sparse vector. Right. Okay, so these are two variables. In evaluation form, what is it going to be? It's okay, so this is 0 0 0 1 1 0 1 1, right? So that's 2. Okay, let me just outline it. Hmm? Right? So our polynomial in evaluation form is 2, 5, 4, 7. Right? Okay. So let's pick values for our tau. What should be our tau of A? 10. Our tau of B? 15. Nice. Okay, so what do we know? Right. We know check 0, check 1, right? Good. And what are we trying to achieve? We want to get an array such that if we do a dot product with the evaluations of this polynomial, we are going to get the actual evaluation of the polynomial at that point. Right? Sorry, which one? It's just a random polynomial. Yeah, we're done with that one. This is a new polynomial in 2 variables. So that first one was 1 variable. We use that to figure out, okay, how can we generate the array that we're going to do a dot product with the evaluations of the polynomial. Right? Okay, so next thing now is we want to generate that other array, right? And okay, let's just generate it here. So what is it going to look like? What is the array going to look like?
It seems like two variables. It's going to be like a product of two stuff.
Okay. Okay.
For instance, this 0 0, I like check 0 for A, check 0 for B.
Okay.
So
So that's check 0 for A. What's check 0 for A? Let's say this is A, B, right? So this is 1 minus A, 1 minus B. Is this what you're saying? Okay, so this is 1 minus A, B, right? This is A, 1 minus B, and this is AB. Right? So this is the array we are going to use to do a dot product with the evaluation form of our multilinear. Okay, so we know check 0, right? What is check 0? Okay, check 0. What is check 0 for x? But that is just basically what you are saying, 1 minus x, right? So the x there, I was trying to give you a variable that you will use. I just asked you randomly what is check 0. Check 0 can be 1 minus x, it can be 1 minus a, it can be 1 minus z. You get? Well, I told you what is the check 0 for x. So that's 1 minus x, right? Okay. So we know this polynomial has 4 evaluation points, and the Boolean representation is this, right? So we have basically 2 variables, right? So for each of these variables, what does 0, 0 basically mean? It means we want something, or want a polynomial basically, that when we pass in 0 and 0, right? 0 for A and 0 for B, we are going to get 1, right? This is just a review of multilinear. In this case, this is 0 and 1, right? 0 for A and 1 for B. So that's basically why we are doing this product here, right? Because of the and. This is 1 and 0, 1 for A and 0 for B, and 1 and 1, 1 for A and 1 for B. Okay. So basically, we want to basically get an array that we can use to do a dot product to the evaluations of the polynomial, right? And this is 0, 0, right? We want to check 0 for A and 0 for B. So that's why we have 1 minus A, which will check for A, which will check 0 for A, and 1 minus B, which is check 0 for B. So this one is check 0 for A and check 1 for B, right? This one is check 1 for A and check 0 for B, and this one is check 1 for A, check 1 for B, right? So with this, we can now generate this thing, right? Array that we'll use to do a dot product. Each element of this array is going to be like a field element. Good and fine, there are multiple, right? But when we multiply them out, we are going to get a single field element at every index, right? Is anybody already seeing where the problem will come in the trusted setup?
No.
Is anybody seeing it already?
Can we come again? So maybe
Yeah.
we see.
Huh? Okay, so let me come again. Basically, in the multilinear trusted setup, right? What is, in the univariate trusted setup, we are trying to get the powers of tau, and we want multiple people to contribute, right? So because of this power of or this law of indices, G to the A B is equal to G to the AB. We take advantage of this in order to enable multiple people contribute, right? But the essence in the univariate case is to generate this array, right? Which is, but in the univariate case, it's actually the powers of tau. So it's not necessarily this. Is, let's say, if our tau was A, this is A to the 0, A to the 1, A to the 2, A to the 3, up to the degree of the polynomial. So this is what we are trying to get in the univariate, like, if we are committing to a univariate polynomial, right? But if we are committing to a multilinear polynomial, this is what we are trying to get. Like, this will be the output of our trusted setup.
Are you talking about the power being negative?
Huh?
Are you talking about the power being negative? Power being negative.
The power for which one? This one?
Like,
Okay, no. Like, anything it wants to be. Like, in the univariate case, our powers of tau is G to the tau to the 0, right? G to the tau to the 1, G to the tau to the 2, G to the tau to the 3, and so on, right? In the multilinear case, if it's 2 variables, right, it will be g to the 1 minus a 1 minus b, right? G to the 1 minus a b, g to the a 1 minus b, and g to the ab. So this is the output of the trusted setup for univariate. This is the output of the trusted setup for multilinear for two variables. Right? Okay. If anybody seen where the problem will arise?
When you raise 1 minus 1 like 1% input, so 1 minus 1 minus 1
Of another person's input.
might not give you.
Exactly. You're getting the point now. You get, because okay, so this is meant to be the output of the trusted setup for multilinear, right? In the univariate case, another person can come at any point and add the person's own randomness, right? In order to do that, what does the person do? You know, these are already points, right? So the person just does this to the the power of their own tau. Let's say their own tau is a, right? So let's say a to the 0, right? A to the 1, a to the 2, a to the 3. Like, they finished trusted setup. This person just came, and the person is still able to contribute to the person's randomness, right? Good. But in the multilinear case now, if another person wants to come and contribute to this, these are points, right? These are points. And if the person is contributing to this, then the person needs to do something like, let's say, to the 1 minus a, 1 minus b, to the 1 minus a, b, right?
Is it possible to do that?
That's the thing, it's wrong, right? Because, but you get the point of this, right?
Yeah.
So the person is trying to contribute the person's own randomness. Let's now expand this, because this thing like this,
That's come to multivariate. It's normal multilinear.
yeah. But wait, let's just do something. Like, what does this actually mean? It basically means 1 minus a, 1 minus b,
Yeah.
right?
Yeah.
Times 1 minus a, 1 minus b, right? Exactly. And it's a problem, you get. So that's why, like, the trusted setup for multilinear is it's not so
There is more than one
yeah, there's more than one variable, so it's not so strict.
What are we supposed to get? Like, what is the right? Like, since we know that this is what people is giving us, what are we supposed to get?
Normally, like, anything we're supposed to get, we're still supposed to be able to express it in the form 1 minus a, right? We're still supposed to express it in the form 1 minus a, 1 minus b, where a and b will actually now be the random values that we are partially evaluating at. But this is not the case.
I don't think. You know that for invariant, we're getting tau 3
Yeah.
But this one now, is it just like 1 minus A, 1 minus B across? Like there's no variation.
See, like this A is the point we want to partially evaluate this original array at, right?
Yeah.
And this B is meant to be the point we want to partially evaluate this array at.
But like, if people doing trusted setup, will they know the value that the verifier or whoever wants to evaluate the behavior at the point that they are bringing their own pattern to what's it called?
No, it will be a point, right? Because every other person that has contributed, the person's own value is basically hidden, right?
Okay, so how come we now have 1 minus A, 1 minus B?
No, but it's still. Is it this one?
Yes. Like, the verifier can basically send any random number. Are you saying that? Because I feel like the trusted setup
No.
is supposed to happen before the verifier says, okay, open at this point.
Yes.
So, but this is looking like as if maybe the verifier has already sent it twice.
Okay,
And then
no,
you now,
no. You know, tau, basically the prover and the verifier, nobody knows tau. Right? So is that tau we are trying to get? But in the univariate, in the multilinear case, tau is not just one variable, right? So in this case we have two variables. So they are going to be two.
making up
They are going to be two different taus. Tau for A and tau for B.
So if they're giving somebody
Uh,
I
a
don't
value,
know.
the trusted
One
ceremony,
thing
like
like-
we have two values or three. If there are three variables.
it's going to be what we're trying to do is to generate this array. This array. Right? And this array is just going to be an array of single field elements. Right? Where each of these values in the array is meant to encode this information. Right? Where each of the values in the array is meant to encode this information. It's encoding this information means that there is a concrete value for A and there's a concrete value for B. Even if we are getting just a single field element. Right?
That means that they are combining A and B in some way. Give us
Yes. Yes.
So A and B are known.
Not necessarily known.
that. But it's not in the trusted setup.
Yeah, in the trusted setup.
I thought that was the issue at first.
I thought that was.
Because no sound.
No, I'm saying, like, when you mentioned whether we can see the issue, blah, 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 I thought the issue was basically like, if you look at the multilinear stuff that had like 1 minus A, 1 minus B, blah, 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 blah.
Yeah.
Going on, like, when they want to add their own randomness, I thought like they don't, like, each of them can't know what A and B would be. So like, to obviously add your own version, you need to know what A and B should be. So I thought that was like the issue. But
So, like, one way to do it will be, because if you want to contribute your own randomness, right, one way to do it would have been having, like, let's say G to the A, right, separately, and G to the B separately, right? And then everybody can come and contribute to this guy, contributes to this guy separately,
yeah.
right? But after we've done that separately, in order to get this single element, that means we need to multiply.
Yeah.
right? So that means this is going to give us a point, x comma y. This is going to give us a point, x comma y, right? By linear pairing. That means in order to get this single field element, we are going to require bilinear pairing. Right? We know what bilinear pairing does. It blows the field up, right? But that's basically why this approach can't work. So you can imagine where we have maybe up to z, like up to z variables. So we are going to be multiplying how many points? Up to 26 points, right? The multiplication, good and fine. You can use bilinear pairing, but come on. Even the normal bilinear pairing they are using in KZG, they are complaining about it. And then you want to do 20. Only you. Eh?
What are they complaining about?
But it's a very expensive operation.
It's not bilinear.
Yeah. But like you can still do it, make it do it, think of it, yeah, 2, 2, 2. Yeah. So yeah, you do the first two, get something in the target group. That thing in the target group times another this thing. So you're continuing like that. Right.
I still don't get what A and B mean. And I still don't get what the people participating in the process segment are going to bring in.
Okay. So A and B are the random values.
Random values.
You know, in the trusted setup, we have tau as a random value. So this A here is actually tau for A. You know, you're picking, since it's two variables, you need a tau for the A variable and you need a tau for the B variable. So this A and B are actually the taus. A is this tau for A and yeah, tau B.
So, but what had you put participating in the process segment?
So, okay, we are going to first talk about like the instantiation of the trusted setup. Instantiating the Multilinear KZG trusted setup is pretty easy, right? Because the person starting it basically have those values. But I want to I also want to be sure that we understand why this method can't work.
Yeah.
I just don't understand. Sorry.
No, it's understandable. Wait. How should we do this now? I feel like I'm beginning to digress. Right? I think let's finish this example. Then we'll now come back and know that, okay, we want to look at process setup. Is that okay?
Yeah.
That's okay, right? So we don't digress far and then coming back here, everybody will. Okay, so let me take all this one. Okay. So back to this point. Right. Does everybody understand how we got this?
Yes.
How we got this? Sure. Sure.
Yeah.
What is the essence? Why are we getting it?
Why?
What is the essence of us getting it?
I want to multiply with the polynomial to get the evaluation of polynomial at a
Good. We want to do a dot product of it and the evaluations of the polynomial to get the evaluation of the polynomial at A and B.
So I have a question. Does that mean for the numeric polynomial, if I evaluate at million and back, it could be quadratic, no matter the power I have, then I find the check of the distance and I do the dot product. Am I going to
Yeah, it should still work. It's pure mathematics, right?
How do you evaluate numeric?
So what is the theory behind it?
Huh?
What is the theory behind it?
The theory behind
Yeah,
it.
that makes it possible.
No, it's just pure maths, right? So let's say we have in the univariate, we have the evaluation at 0 and the evaluation at 1.
Yeah, let's say we have a quadratic.
Say we have a quadratic,
Yeah.
that will be the evaluation at 2. Ever? Yeah, because it's a quadratic.
So quadratic for univariate.
So in a quadratic,
Yeah.
you need 3 points to represent a quadratic.
Okay. Zero
Right.
and two,
0, 1, 2. Right. So you now need to do like check 0, check 1,
Check two.
check 2.
Ah, it's okay. Check two will be 2 times check one.
No,
I is check two going to
check 2.
be. Okay. No, I know it's going to be.
Check 2 are interpolating sets now is 0, 1, 2.
Yeah.
So even at check 0 will change.
It will have 1 and 2.
Yeah, it will have 1 and 2.
When
Even
I
at check 0
Zero will be 1
will
and
no
2.
more be 1 minus x.
Yeah.
Right.
Yeah.
At check 0 will change. At check 1 will
I'll
change.
Check 0 and 2, then check 2 will be 0 and 1.
Exactly.
So are you sure when I multiply it?
I haven't tried it, but this math it should work.
Why does it work? What theory behind this?
It's Lagrange now. Right?
The Lagrange I know is not.
This one will give it
No, not like this method.
to
No, this method. Wait, this method is work for multilinear, like the power of power. The way the basis multiply by this. I'm not taking. Do you see how we did our I'm asking that if I do the same method for the would I get the same answer?
See, what is if you have the evaluations of a univariate polynomial and you want to get back the coefficients,
Yeah,
how do you do it?
I've never tried that.
It's Lagrange now.
If I come again.
You have the evaluations of a polynomial
Okay.
and you want to get back the coefficients.
I want to get back the coefficients.
Yes.
Okay, Lagrange.
It's Lagrange.
Yeah.
And what is Lagrange? Lagrange is y times the Lagrange basis,
Yeah.
right? Y times the Lagrange basis of like L0,
Yeah.
where the array we are using to do this is basically our y values, y0, y1, y2,
I get it.
and then this is basically our Lagrange basis, L0, L1, L2.
I understand.
Makes sense,
Yeah.
right? So it's basically just Lagrange.
I get it.
Okay.
So, sorry, if you don't want to use Lagrange, now we do it with like just the coefficient multiplied by reference rate, which is what we call
Yeah, the coefficients.
product.
Huh?
I said the coefficient multiplied by the power.
By the powers of x. Yeah. Well, that's when you're looking at it in the coefficient form now.
Okay, thank you.
Yeah. I hope it makes sense.
Yeah.
Yeah.
The question is, when we multiply that, this check 1, check 0 of the indexes of the evaluation form,
Yeah, it's this one, right?
yes, when multiplied against the evaluation form itself, like, what's the name of the thing that we get?
That's basically like it's the evaluation, right? But you can still think of it as it's still Lagrange,
Okay.
right? It's still Lagrange because
Yeah.
in that case, y0, these are our y values, right? These are our y values. And what is Lagrange? Y times the summation of y times is Lagrange basis. So these are basically the Lagrange basis values.
Then when you multiply it, then like, when you multiply it, what's is it like the evaluation of
Is it when we multiply? Is it when we have concrete values now?
yes?
Yeah, it's the evaluation, the actual evaluation of the polynomial at because
Points.
yeah at this point A and B. Okay, because we are going to multiply it and also sum, right? When is the Lagrange like basis? So when we think of this as polynomials, when we do the multiplication, we are going to get a polynomial, right? But if we now fix the value for A and B, it collapses down to a single value, right? But if we have already done the Lagrange basis and we now have a single value, we just need to do a dot product and a sum. Yeah? Like, sorry, we just need to do a dot product, yeah, to get the evaluation. Seems a lot of people are lost. A lot of people are lost, right? What is a polynomial?
Polynomial is an equation that has a variable with its coefficients. It's an equation.
Right. So you can basically think of a polynomial as a sum of terms, right? Or a sum of monomial, right? Am I confusing you people?
No.
Eh? Are you sure? We can think of a polynomial as this, the summation of, let's say, yi from I equal to 0 to n, right? Yi times the Lagrange basis of I. What should we use to denote Lagrange basis? We can think of a polynomial as this. Do we agree?
Yes.
How? Why do you agree?
Because
That is,
Huh?
that is,
No, you need to know why.
that is Lagrange. This is Lagrange.
This Lagrange,
Yes.
right?
Yes.
So why is the evaluation
this
this?
the set of points.
Mhm.
So you have the set of points, which
Yeah.
are basically like your terms.
Yeah.
So when like your Lagrange basis is basically let's say from fitting based on like 0 and 1, like we're trying to evaluate them, right? So once we basically do that multiplication and sum them over to a specific number of points, right? We get that polynomial that defines this.
Right? So basically, like you can think of any polynomial, whether it's univariate, whether it's multivariate, whether it's it just came to my head now. Like whether it's univariate, whether it's multivariate, whether it's multilinear, you can think of it as this, right? The evaluation times the sum of the evaluation and its corresponding Lagrange basis, right? So that's just basically what we are trying to do here, right? That's just basically what we're trying to do. So this is the values for y, and this is the Lagrange basis. So we're doing it element wise. So 2 for 2 here, this is its Lagrange basis. For 5 here, this is its Lagrange basis. For 4, this is its Lagrange basis. And for 7, this is its Lagrange basis. Is it making sense?
Yeah.
Are we sure? Okay. So I think like everybody will need to go back and review like polynomial. Huh? Again. Just look at the polynomials again. Right. Just look at the polynomials again. But if this makes sense, then this should make sense. It makes sense, right? Okay. Okay, so let's continue. We had our values of, I thought we picked the values for tau already. Okay, these are 10 and 15. So initially this would have been an array of polynomials, right? Which is the Lagrange basis for each of the evaluations, right? But now we want to collapse it to a single value, right? So I want to evaluate these polynomials at tau of A and tau of B. Does it make sense? Okay, so let me just copy this. That's going on. Okay. So this was an array of our Lagrange basis, right? But we want to now evaluate the Lagrange basis polynomials, right? So this will now be 1 minus 10, 1 minus 15. This will be 1 minus 10 times 15. This will be 10, 1 minus 15. And this will be 10, 15. Right? So what is this going to be? It's minus 9 times minus 14. Right? So what is that going to be? That's already help us. Huh?
1 to 6.
1 to 6.
1 to 6. So this will be minus 915. That's minus 135. This will be 10 minus 14, right? And this is 1050. Okay, so if this were our values of tau, this is what we will be expecting, right? After our trusted setup, we'll be expecting g to the 126, g to the minus 135, g to the minus 140, and g to the 150. Right? Yeah. So makes sense, right? Okay. So now we have these values. We want to evaluate our polynomial at these values. Okay, yes, I'm going to. I was just.
This G is to the power, they are the powers of the power.
Yeah, you can think of it that way. So they are the powers of tau for the multilinear case.
But
Yeah.
what is it called in multilinear?
It's still powers of tau. Same trusted setup, right? Makes sense, right? So now we want to evaluate our polynomial. What was our initial array? 2547. 2547. And we are doing a dot product with 126 minus 135 minus 140 and 150.
This is us trying to evaluate
The polynomial, yes. So this is us trying to evaluate the polynomial at A and B, which is 10 and 15. Okay, so what is this going to be? Huh? That's 252, right?
Are we not supposed to add?
No, we are going to add. Yeah. It's minus 675, right? Minus 550. 60, okay. And 1050. Okay. So dot eta dot sum. So what is our answer going to be? $67. So this is our commitment, right? This is our commitment. Makes sense? So that is basically the evaluation of our polynomial at That's basically the evaluation of our polynomial at tau of A and tau of B. Yes. Should we confirm what was the polynomial? Huh?
Okay, plus 2.
Yeah. 2A plus 3B plus 3B plus 2. 2A plus 3B plus 2, which will be 2.
Correct.
Yes, correct.
Okay. Makes sense, right? We can scale this up to as many variables. With this, eh?
I never knew Lagrange is stuff.
Actually. Actually. So, this is what, like, the process in order to commit to the polynomial, right? This is how we commit to the polynomial, right? And we can remember the normal polynomial commitment. You commit to the polynomial, send the commitment to the verifier, right? And after you send the commitment to the verifier, what does the verifier do? The verifier tells you open the polynomial at this point, right? So in the multilinear case, we have more than one variables. So when the verifier is opening the polynomial, he's going to tell you open the polynomial at, he'll give you a value for each of the variables, right? Then what does the prover need to do? The prover evaluates the polynomial at the points the verifier said. He gets the result v, right? And what else? He needs to also generate a proof, right? He needs to generate a proof that v was correct. Are we all together? Okay. So the polynomial commitment, like any polynomial commitment, the prover commits to the polynomial, right? The verifier tells the prover open this polynomial at this point. Then the prover will now send back the evaluation of the polynomial at the point the verifier said and a proof that that is actually the evaluation of the polynomial. Makes sense, right? So for now, we've seen how to get the commitment to the polynomial, right? So we get the commitment to the polynomial, we commit to the polynomial, right? So the next thing will be the verifier picking points that he wants to open the polynomial at. That one is pretty easy, right? Just pick points, send it to the prover. The prover knows the polynomial, so the prover can just evaluate it at the points the verifier said to get v, right? He sends v back to the verifier, and now he needs to generate a proof that v is actually the evaluation of the polynomial at the points the verifier said. Now let's look at how does the prover generate the proof. Right. So after looking at how the prover generates the proof, then we are going to stitch everything together. Does it make sense? Okay. So how does the prover generate the proof? In the univariate case, how did the prover generate the proof?
Yeah, I think he first found Q of X first.
He first found
Q of X, the proof polynomial.
the proof
Yeah,
polynomial.
multiplied it with power.
Power.
Q of tau.
Yeah, with tau. With powers of
Q
tau.
of tau.
To get the evaluation of polynomial at tau.
Yeah. So the major work the prover is doing is getting that q of x, right? And then we can now evaluate q of x at tau, right? So in the univariate settings, how does the prover get q of tau? Q of x, sorry. We know f of x minus v over
X minus
x minus a is equal to q of x, right? This is the univariate setting, right? How about in the multilinear setting? F of x, we know f of x is a multilinear polynomial, right? So we still have our f of x, right? We know v to be the evaluation of the polynomial at the set point. V is always still going to be a single element, a single value, right? How about q of x and x minus a? X minus a would no more be 1, right? Because we are going to have x minus a, we are going to have x minus b, x minus c, up to the setting, yeah. And also, like, how about q of x? Hmm? Comma c. This?
So if you have f of a, b, c, like on the left, and dividing by x minus a, I mean your q should be q of b, c, because I think a should be eliminated.
Okay.
X minus is like a factor.
Okay. Since x minus a is a factor.
Yeah.
Okay, so let's outline what people have been saying. What you people have been saying. Let me emphasize. Okay, so this f of a, b, c, right?
Yeah.
Minus v, right?
Yeah.
Then want to divide by x minus a, right?
Sorry, what is B?
V is the evaluation
At what?
at ABC.
Then isn't
That's what
the
At ABC.
denominator supposed to be x minus a, x minus b, x
So the q is going to
Because
be a
when
q
we
of
just
because a is gone, right?
Okay.
Wait, AC remain the factor.
No,
I know what it's
same is forever.
So this will be Q of BC
Suggestion.
I don't think so.
plus R, right?
Yeah.
Okay.
R of what? Where R equal to 0 if what? Eh?
X minus a is a factor.
If x minus a is a factor.
That is one.
Eh?
Like the idea of, I don't know,
Now I feel that,
the factor thing.
The factor thing.
see, since it is supposed to be x or divided by x minus a, x minus b, x minus
X divided by
no, I have f of
Okay.
ABC minus b over x minus a, x minus b, x minus so it will be discretely be equals to q of
Exactly. And if then if it is
so it will be Q of what?
then R of whatever
If you are doing the
That means Q is going to be 1. Yeah,
wait,
Q of x now.
if you are doing this way, sorry. Wait, we are wait. I'm confused because we are not supposed to even have f of ABC because over the this thing. Please change the this thing.
So it should be
Change
f
the
of
variable.
x, right?
Use x1, x2, x3.
or X, Y, Z.
It's still the same thing.
That's what I'm saying.
X, Y, Z.
So then change that one to X1, X2, X3. It will now be Q of X1, X2, X3. Yes, that is it.
Okay.
There is no house. There can't be house.
Except for the color.
Because we're evaluating B at X1, V at X1, X2, X3. There can't be house.
Interesting. Okay, let's try to prove this.
Okay.
Okay, so it's actually correct. But let's prove it. Let's prove it. Is it correct? Okay, let's prove it. So which polynomial should we work with? 2ab plus 3bc. Wait. No, let's work with something we already have.
So let's work with this 2A.
2a plus 3b plus 2.
So that will be X1 and X2.
Yeah, let's just. It's still the same.
But there's no C.
Yeah, no C.
So it will be 2B.
Yeah, so very. Okay. So what you're trying to say is that this Q of x1, x2, x3 is a single field element for all of them, right?
Yeah.
Okay.
That is supposed to be a polynomial. I don't think polynomial. So when you evaluate the value,
It's not correct.
it could be as
No,
well.
what I said is not correct. Do you know why? It's not correct. Should I tell you why?
Bye.
Because what I said can only work for multivariate. It can't work for multivariate. Because
Why can't it work for multilinear?
yeah, it won't work for multilinear because
Explaining this one already, we have a cubic equation. Like the denomination.
Like BB1.
The denomination already, they have
The
a
denominator.
it won't work for
How?
multilinear. It will work.
X1, X2, X3, we give
It
you
won't work.
a
I
There are
get
different
There are
distances.
different
It's not-
x's.
there are different
Yes.
distances. That's why you have the x1, x2, and x3.
But all multiply together will still be a cubic.
Let's test it out.
So, just different values of how
Well,
you
you
want
already
to
said
use
it's correct.
Let's test it.
Eh?
You guys, I said you already said it's correct.
Is it?
You already-
Let's try
Eh?
it.
Is it correct?
I don't
It is. I think it is.
Is it?
Yeah.
But that be okay. That be okay.
Let's try it out. I'm doubting it.
Okay, so let's see. These are polynomial, right? 2a plus 3b plus 2. And at our, or let's say our a is 10 and our b is 15, right?
But this is not factorizing.
This polynomial.
Yeah.
It may be factorizable, maybe after subtracting it from B. But let's take them down.
Yeah, let's just calculate that and just follow the process.
I'm waiting for
So if we partially evaluate 10 plus 3, 15 plus 2, what was the answer here?
67.
67,
Yeah.
right? So f of let's say AB, right, minus V will be 2A plus 3B plus 2 minus 67, which will give us 2A plus 3B minus 65. Right.
Yeah.
Okay, good. So now this polynomial, we want to divide it by what will be our denominator?
A minus 10, A minus 15.
X minus
A minus
10.
10, A minus
Okay.
A minus 10, B
Yeah.
minus
B minus
15.
15. This is our denominator. Okay, let's expand.
Oh,
Okay, let's divide it one by one. Right. So this is 2A plus 3B minus 65. A minus 10. Right. So this will be 1, right?
can you divide like that? Let's use partial fraction to separate, then we'll not divide. I don't know, I'm just thinking that.
It's 2. Like, you know what?
No, it's like so this. Sorry, 2. So 2 times A is 2A, right? Minus 20. So this guy goes off.
How does it want to divide?
3B.
You won't.
Yeah. No. So this 3B minus what? 25. 45. So this is our new polynomial, right? And this new polynomial now, 3B minus 45, we are going to divide it by B minus 15. So this is 3, right? This is 3B minus 45. Right? So,
Can we do this in math?
huh?
No, like, can we divide this way? Two variables.
Uh-huh.
I've not done it.
Yeah, multiply now.
Okay, good.
Yeah, multiply.
So,
Let's not
what is
whether
this?
we get
This is our
the
Q
quotient.
of X with respect to A, right? And this is the quotient with respect to B, right? Okay. Okay, so this is our remainder after dividing by this first guy. So let's multiply. What are we multiplying? We are going to multiply the quotient by the divisor.
What was our remainder?
I mean, that was 3B.
This will be minus 4.
There's no remainder now.
There is
No, for the first.
For the
Yeah,
first
first
one. Yeah. So we are going to have two into A minus 10, right? Plus this 3B minus 45, right? Right? So what is this going to be? This will be 2A minus 20 plus 3B minus 45. So what is this? 2A plus 3B minus 65.
Is that what we are?
Yeah.
Wait, how did you multiply that? I don't know to do A minus 10 multiplied by 3.
No, we are going to add the remainder now. We multiply Q of X times the divisor and then add the remainder. Right. Okay, how about this other guy?
Sorry, let's treat like reverse engineer. Let's divide first by b minus 15. Then this thing will
Get
now
the
say
same thing.
a minus 10. I'm just saying.
You get the same thing, it's
I'll be
partial
done.
division.
Wait,
Have you done
you
it?
said let's divide first
By
by.
yes, the other way, b minus 15. Instead of divide by a minus 10.
Okay.
Let's see.
That is the 3b minus 45. Let's divide it by.
No, you say let's divide first by b minus 15.
Instead of
Instead of
minus
a
10,
thing.
one will be first. We should do
No, motivation is commutative, so it can go anywhere. So if it's not,
Give it
it's
to a
not
minus 20.
do you get
If you do it that way, it will give a different
A
Q.
difference, something a minus something.
Is it not supposed to
You
be
get.
the same? Since motivation is commutative.
It's not actually the
You
same.
give to a minus 20.
Do you get what I'm saying?
It's
For
with
example,
respect to the variable we are using.
do you, for example, let's forget about variable or whatever now. This division theorem is gotten from normal division we know before, from numbers. So you get, for example now, if I have 30 divided by 3 times 6, are you getting that? I can go by doing 6 divided by 30 first, or 3 divided by this thing. Irrespective of the path I take, I must get the same output.
You get the same final output.
Yeah.
But you say
Yeah.
you say 30 divided by 6.
No, 3 times. I think you said 6
Three
times
and
2 or
two
3
times
times 6.
30 over, let's say 3 times
3 times 6.
6. Or let's say 3 times 2 rather. And now I can say 2 in 30 first.
Mm-hmm.
Right? And then I will now do 3 in this. It will give me the same output.
Yes.
Right? Irrespective of the one I
The one you
am
started
doing,
with, yes.
So I'm now saying that since we started with a minus 2, can we start with b minus 5? Then let's see whether we still get the same answer.
If we do b minus 5,
Yeah.
what we're now going to get, the remainder, there will be no b in it, right?
Then we'll now do a minus something.
Yeah. If we do that, we're still going to get 0 as a remainder. But let's do it.
Let's try it.
We're still going to get 0 though. The both of them are factors. You get. So anyhow, so this is 2a plus 3b minus 65, right? 2a plus 3b minus 65 and b minus 15, right? So this is 3, right? This is 3b minus 45, right?
2 minus 20.
So this is 2a minus 20, right, as our remainder. So this is 2a minus 20. When we divide by a minus 10,
That would be 2. 2 minus 0.
that will be 2, right? You see, right? But our q, now we got this one first. We got the 3 first before we got 2. So that was just the thing actually.
My conclusion, however, is how is a minus this, a minus 10 and b minus 15 the factors of that equation when we don't have ab in the equation?
The factors of
Like go back to that. Go back. Oh yes. No. Where's the main equation we were writing?
Down. Wait, no.
uh,
Now when you
Yeah,
write it
stop.
out.
Stop. Stop, please.
Yes. So like this now we don't have A B here. We only have A, we
How
have B.
how don't we have AB?
No, like we have A, we have B. We don't have A and AB together.
Oh, it doesn't.
You don't get what I'm saying? If
Like we
expand-
don't have AB together.
Yeah, we don't have A B. We have A.
Does
we have B.
that matter?
Yeah, but the factors now, if you should expand this now, we'll get something like an AB.
How?
If this A minus 10, B minus 15, if we should expand it, we'll get the first value we get is AB.
You say
Then before
A minus 10, B minus 15.
15. If we should expand it, we'll get AB.
Yeah. So that is actually where this thing is wrong. You get? That is actually where this thought process is wrong. You get? That's actually where it is wrong. Because if we multiply this two, we are going to get AB.
Yeah.
So the thing is, when we want to divide, we divide one by
One by
one.
one, yes, that works.
We divide one by one.
Yes.
So if it happens that we have, for example, questioning what you have done because it's catching my head. I have an idea before of something like this. When we have something like this, what we normally do, what I know before is just do partial fraction to separate and divide. But now you are doing this, which is new to me. So questioning it, I gave myself a new polynomial, and I want to do same thing, whether I get it. So, but I have a type, such that the polynomial I give myself is 3ab plus 4c
3AB
plus 4c.
plus 4C.
Yeah.
Okay.
So can I divide something like this, where my a is 1, b is 2, c is 3?
Yeah. You can. You know, the first thing is we need, if you evaluate this polynomial and it doesn't give 0, then
If we give 0, since we are subtracting from, that is the point of subtracting.
that is the point of subtracting V,
from
right?
the
So
polynomial.
once we subtract V, then when you divide by the factors,
Yes.
eventually the last remainder you are going to get will be 0.
0.
Yes.
And
If that last remainder is not 0,
Mhm.
that means it's not, like, the V is not a correct V.
Let's try it.
Okay. But is everybody with us? Like, is everybody following? Is everybody following what we are doing?
You're still gonna
Yeah, you were
get-
saying that something
It's-
is
it's
not
still gonna
correct,
lead you to
that
the
a
same
particular idea is not correct.
There's no easy.
Okay, that was this.
We'll be able to divide separately.
Partial fraction is just dividing that denominator.
So we can't say multiplying all this through, right? In order to now get one polynomial and to do this,
Or the division one.
the division once, yeah.
But like the way we're dividing each polynomial is correct.
Yeah, like one by one.
What's the suggestion?
It may actually be, but let's see.
If you actually
If we-
multiply them at once and divide, you should get the same.
It should be the same
Yes,
thing,
it should be
right?
the same thing.
But
But then
okay,
we're
let's
now going to
let's
like
let's actually do
the-
that.
the zeros.
Let's actually do that also.
I'm thinking
So this is a minus 10 and b minus 15. So let this guy wait. Right. So this a minus 10, b minus 15. Based on mathematics, like it should actually like be the same thing, right? Like multiplying this through. But the thing is, we are looking for a way that we can actually represent it in code. You get? So it's not just about like good and fine. The maths may work, But how do you want to represent it in code? How do you want to build a protocol on it? Right? So this is b minus 15, right? And so this is ab plus 150. So let's start it with so we'll now be dividing 2a plus 3b minus 65 by this. 2a plus 3b minus 65, right? How about dividing by
Zero.
Why? Who
Eh?
said
One, can just put one there, multiply one by
Zero.
one.
Why is it one?
wait,
One can go in
When do
there.
you see it?
One, basically. If you put zero, then you spoil everything. It's one.
That's what I'm
Hey,
saying. When do you see it here?
So you go is where you put one and multiply the subtract.
Subtract from
Okay.
what?
Because
So-
the only one you put one is if AB divides something, then
Where is AB? What's
so this is even problematic, right?
Very.
This is even problematic.
No,
So
How do you want to
yeah. So like but if you want to divide them like one by one, that's pretty easy. That's pretty easy.
Yes, that's
Right.
that's gonna be.
And
if you say A divided
It's almost as if we can write out that
Let's try,
a minus
let's try
10
it.
and b minus 15 and then
which one?
Yeah,
minus
this
AB.
is one.
We are going to get
So-
minus AB and
So this will be
And then it will work. That's what I'm saying now.
how will you work?
okay.
So
So
subtract, you will not compress everything together. Then
so minus 15a minus
zero,
10b,
everything will go slow.
right?
Where is the one?
No, I'm coming.
I think the thing should come to the left more so that A can be
Yeah.
under 8.
But it's 2a plus 3b plus what was that?
Minus 10b. Sorry.
Minus 65.
Minus
Right? So this AB minus 50 minus plus 150. So if we subtract, we are going to get minus AB right plus 2A. Let's
Minus
Plus 17A.
okay, let's do the ones down.
Plus 17A. 2A and 15A.
Okay. So that's
17A
plus 17A
plus 13A.
plus 13b.
Plus 13B, sorry.
And minus 215.
Minus that should be
215.
okay.
Now what?
So one is the quotient, while every other thing is the remainder. So this work, the law that behind this can work is division algorithm. If I have A divided by B and give me C, or let's say A and B are co-prime, at least one will go. If I have the GCD of A and B and A and B are co-prime, it's
But-
fine.
But what do we
What is
succeed
this?
in
What
this?
are you guys trying to do? What are you trying to achieve?
Exactly now.
What did we?
Okay. Let me tell you the importance of this thing now. what she said, actually, I wanted to give up on what I was doing before, which also question the formula we are using. Now, consider this equation polynomial 3a plus 3ab. This one cannot go again. You can't do
You are the one that
anything.
said we should continue with this one first.
I'm not the one that said that. Right?
No, but the reason why you
Okay.
the reason why you say
See.
one.
See, everybody,
You said one.
one will always go, right?
This go again.
One will always go.
Why we always go with
Okay,
everything, not zero?
One will always go with everything.
But what's the basis of putting one?
Just
Wait,
count.
we wanted to prove that if we could do this separating a minus 10 and b minus 50
Okay.
separately, we will get 0, right?
Yes.
So he's saying
And we did
said
that and it worked,
that
right?
if we combine a
Yes,
minus
that
10,
one.
b minus 15 together as one polynomial and we divide it by this, we should also get 0 as the remainder, yes?
Yes.
Now let's get 0. Simple. Let's not go to any other polynomial till
No,
we
you
get
want to
0.
use no, if you work.
Like,
Let's get 0 now.
we can't,
Their side to work.
we can't move from here now. What are we expecting?
It's right.
If
What
you
you
want
do one again.
No.
Okay, wait, let me
See,
if you don't
wait, people should calm down. Like, listen, like, all of we're learning, right? Me too, I'm learning,
Yes.
and ahead now because
If you because
because
Dividing by one.
you can get minus one.
By the 8
by multiplying with
Minus
a,
one, you go back to 2a,
No, go
plus
back
3b.
zero.
you just keep doing
No, you go back to 2a, like under.
Yeah, you go back to
2a
2a,
plus
but then
3b.
the thing now is that
That
with
one goes to 0.
multiplying through we have gotten a new term, ab,
So how does
right?
that work?
And how can we remove ab when we don't have a term that is ab that we are multiplying by? That's a problem,
Okay.
right?
So what better this is what that I suggested the formula and I said it was wrong. Yes.
See, nobody. We're not playing. We're
No,
not
no.
blaming everything.
No,
We're actually
I'm-
just testing.
Yeah, I want to. So
Sorry.
I'm not trying to test what I said before. Why it's wrong. So it worked for the first one we did, and I was like, why did it work? Is it because we don't have the time? You know, I was saying the question that you raised before this girl now brought another thing. You get my point. So the reason why I'm interested in this question was that I want to see how it's going to be, then I'll be able to. I've started solving the question I gave you that I said you will come back to me. I started solving it. I'm just stuck exactly the same point as this. So
Are you multiplying through?
I'm not multiplying two.
You're doing it separately.
I'm still doing it separately, but my polynomial has a type,
Okay.
not my dividend.
Okay.
So the polynomial I have,
Okay. So let's look at it.
together.
So
So you will now
the-
appreciate
this
what
one- this one doesn't go past this place. Like, oh, we agree, right?
Yes, we are.
So
agreed.
I don't know why it doesn't go past.
you can actually.
That's the thing. Why doesn't it go past? Because AB still has AB. Let's
So you can
even
get
if
minus one.
let's do
Okay.
it at least. Even if we are coming back to that 2A, we now say it's because we are coming back to it that I can't go. But
Okay.
I'm seeing AB.
Okay. Actually, so let's remove this one, right? This 2a, right? What can we multiply with minus 15a to get 2a? What is the idea? The idea is that we want this guy to go to 0, right? So that we can get a quotient, right? So in order for him to go to 0, what can we multiply with 2? What can we multiply with, say, minus 15a to get 2a?
That's going to be a fraction.
That is 30 over.
That's
30
a
over.
fraction.
Yeah, it can be a count.
Yeah, it can be a fraction. So we want to get 2a, right? We're looking for what we're going to multiply with minus 15a to get 2a.
That'll be 2 over.
Multiply,
2 over minus 15.
multiply 15a by 1 over 30.
right?
Yeah.
So if this guy, this will be minus 2 times
Yeah.
minus 8.
Minus 2 over 15.
Minus over.
So minus 2 over 15, right?
Mhm.
So if we multiply minus 2 over 15 with everything here, what are we going to get? So that's,
Minus 2 over 15.
okay, so let me just bring it out here. Minus 2 over 15 AB, right? Then this minus, this will be plus, right?
Yeah.
Plus 2A, and this will be plus,
Plus 20
Nice.
over 15.
Yeah.
I like 4 over
20 over 15B, right?
Yes.
And then minus,
That was like
as
20.
150, or let's say 300 over
300 over
15.
15.
3. That's 20.
That's 20, right? And this guy is 4 over 3, right? Or, okay,
So we want to remove B now. After one.
so what are we going to get? Minus 2 over 15 AB, right?
Yeah.
We're, we're subtracting, sorry, this will be plus,
Plus,
yeah. So A has gone, right?
yeah.
This will be,
3 minus 4 over 3.
Minus
Yeah.
5 over 3.
that's 5 over 3.
Minus 5 over 3. No, no, plus, plus. 5 over 3.
Then minus 0.5.
Minus 45, right? Okay, so what's next?
Let's go for B.
Let's go for AB.
Let's go for B.
Let's go for B. Okay, so what are we going to multiply with minus 10B to get
5 over 3.
5 over 3B?
5
Hmm?
over
Let's
6.
go 15. Yeah,
Oh, I
for
see.
16 makes it close. I just take the in.
Want to get 5 over 3B, right? We have minus 10B. So
1 over 6.
Minus 1 over 6.
right.
Minus 1 over 6.
Will it? Okay. So that's minus 1 over 6, right? It's minus 1 over 6, so. And these are two constant values. They are going to collapse. Right? These are two constant values. They are going to collapse into. I don't know what to solve. Let's solve. Okay, so this will be minus 1 over 6 AB, right?
You're not bringing back the
You see, you're not bringing back the A again. So, like, let's just end it here. Let's see, like, no, seriously, I agree with you. It's actually. No, but actually, like, it's supposed to work. This maths, right? Wolfram Alpha. But there's no need. Let's just move forward,
Then,
please.
but then just like confirm that we will actually get to the same thing.
Huh? Power.
Is it the time?
Oh. How low? Okay, so okay, so at our spare time actually we can continue. Eh? At our spare time we can continue. But let's
That's what's it called now? What's that website? We can do this thing. Yes.
No, that's it.
Let's try it.
Sorry, what did
Wolfram Alpha usually
You take a call.
I actually have issues accessing Wolfram Alpha.
You take a call. He said Ines, that's my
Oh. Okay, so what is it going to be? That's 2A, sorry, 2A plus 3B plus 2, right? Sorry, minus 65 divided by A minus 10, right?
Write the full polynomial.
No.
No, we don't see the full.
yeah, right, the
You don't see this one.
expanded polynomial
It's
instead.
funded in fight.
Why they expanded? But it can still do it now. It can still do it.
You want to see that expanded one, whether or not
Okay, so what is it?
What if expanded?
AB minus 15.
That's A factor.
Sorry, AB minus 15A, right? Minus 10B plus 150.
not possible.
Okay,
What's the answer?
Oh, we have the steps.
Zero.
Which of them?
okay, so this is actually like, you know, we gave it this, so it's factorized it already for us. So this is, yeah,
Expanded
Integration
What
formula.
is the answer?
What is the answer?
I think this should be the answer.
No, it's step by step
Zero.
solution.
It is not even.
The same way A minus 10.
What is step by step solution?
But I don't think you gave a succinct answer. Not succinct results.
This is just the input.
Yeah, that means you have to like take it back and read the results.
No.
Hmm.
Splitting it into different fractions was never an issue.
Okay, this is it.
Where is it?
So
Well, it's found in
it's not equal to 0. And then this, that's for A. A minus 10 is not equal to 0. B is equal to this. So
Is that what we
But
have to do?
that's not what we asked it to do.
Yes.
So please,
Let's have
at our spare times, we can go back and cut. Eh?
You just threw you off now. You really want to get it. You threw you off for a lie.
Okay, but what's like all these things we've been doing basically is just we know dividing one by one, dividing by the factors one by one works, right?
I still question that.
Okay, bring.
Okay. 3 AG.
So 3AB
Yeah. Plus.
plus what?
Let's say plus the
But
contract plus
sorry, before you continue, you gave a scenario where you give like 30 divided by 3 times 2 or something. And you said the same thing if you divide 30 by 3 first, whatever it gives you, then you divide it by 2. It's still going to be the same thing. So if you want to follow that same scenario, I think this should work basically.
So now, all what we did before was in R. The normal division, this thing that you
See, okay, just give me
okay.
a value
Let's
for
say
A
A is
and
1, A is 2, B is 2,
A equal to 1,
B equals to 2.
B equal to 2. So first of all, what are we supposed to do?
We have
We're supposed to find V, right?
Yeah.
So this is 3, where A is
6 plus 2, that is 8.
right. So our f of AB minus V will be 3AB plus 2 minus 8, which is 3AB minus 6, right? 3AB minus 6. What are the factors we're supposed to use? A minus 1
Yeah.
and B minus 2,
Yeah.
right? So if we divide this guy, this is 3AB minus 6. We divide it by A minus 1.
It's going to work. Let us divide it by
Right.
a product of.
Calm down.
I will
It's gonna
So
work.
this is 3.
Yeah, this 3.
This is 3A, right?
3B.
Sorry, 3B. Yeah. So this will give us 3AB minus 3B. Right? When we subtract, what do we get?
3B.
We get 3B minus 6. Right? So with 3B minus 6,
Oh, plus 3.
we divide by B minus 2. Right? So that's 3. 3, that's 3B minus
Minus
6. And when we divide, we get
Otherwise, let's just do A minus and let's expand that
That is
once.
not-
And we do what we want to do. And check what we want to do.
Okay, Papa.
So what is the point?
so what was where were you having the challenge?
What the point I'm making is that
Sorry, where were you having the challenge
the
first?
challenge this is not the question I saw actually. I just did it. Mine was 3B. I had C.
Even if you do 3 variables,
So
it will still work.
When we have time, don't worry.
When we have a tie.
Don't worry. Then let's continue with the
Wait,
class.
you have time now.
This example, I not carefully think about it. I just do that.
I think why it was expected that you give us that particular example that was the so that we can just like we won't be able to run.
Don't worry, let's continue. I will.
Okay. So basically like out of like after everything we've done so far, right? What have we figured out? We figured out that if we have a polynomial, right, and we want to open the polynomial at a point, if we partially or if we evaluate that polynomial at the points we want to open the polynomial at, we are going to get v, right? And just basically still the same KZG formula, or still the same polynomial equality formula. Let me stop calling it KZG formula, right? Where we have f of x minus v, right, is equal to q of x times x minus a, right? So still the same formula. When we get v, if we subtract v from the polynomial, we are going to get a new polynomial that when we divide by the factors, we are going to get a 0. Do we agree?
So I can take that in.
So basically we know this is the univariate case, right? And in this univariate case, when we subtract the polynomial by v, a automatically becomes a factor of f of x minus v.
Yes.
When we are now dealing with multiple variables, right? When we are dealing with multiple variables, then we have a situation where we still have f of x, right, which is the original polynomial. And when we subtract v, we are going to get q of x and x minus a, right? But then this is now going to be a summation over the number of variables we have. We are going to do an example, right? This is going to be, let's say if we have okay, I equal to 0 to n, where n is equal to the number of variables.
So our Q change.
Yes.
Huh?
Our Q change.
Yes.
Yeah, so we are going to have, yes, yes.
Yeah. So it's kind of like
And here is the Y Q change.
We did an example, right? In this our example, this is q with respect to a, right? This is q with respect to b. So each of them is going to have their own quotient.
I get.
So at the end of the day, that means that if you have 3 variables like A, B, C, using that one, we'll first sort for A, and when you are done, sort for B. Sort for C.
When you partially evaluate at a variable, you're going to have a new polynomial in half the number of evaluations. Basically, a new polynomial with one less number of variables, right? And sorry. And we continue doing like that basically after partially evaluating. The new polynomial that we're going to get as the remainder of the first one, we partially evaluated at the first variable. We get a new polynomial. That new polynomial now, that's the new variable we're working with is going to be a factor of that new polynomial. So we divide again. We get a quotient, we get a remainder. That remainder is in a new variable, like one less the initial number of variables we started with, right? And the let's say the variable now that we're partially evaluating at, the value that we're using to partially evaluate is going to be like a root of that remaining polynomial. I think, like, let's just do an example. We've done multiple examples, but then those were like just experimentation stuff. We've done multiple examples, but those were experimentation stuff. So we're now going to do like a new example and actually generate the proof for a polynomial step by step so that everybody can follow. Does that make sense?
So, explain.
Sorry.
So like my question is, for if we have to follow that formula, does that mean that we have to get all our points, all our evaluation points down? Because if we should have, probably maybe we should have the evaluation point of A, that means we have to definitely get all our evaluation points down, because that's how we can get V and then start the equation. I think.
You have answered your question,
Yeah.
right?
Yeah, I guess this what you wrote down now is trying to explain why this works for the multilinear, right?
Why?
This works for the multilinear.
Yes.
Because the multilinear is just another multivariate, right? It's still a multivariate, just like the special type of multivariate.
Yeah.
And the fact that each of them have like different quotients. Like that's why when you're doing like successive divisions, when you divide one, you get different quotients. And when you divide another one, you get different quotients. But for me, what I'm trying to say is that remainder part. That remainder, you said something like when you divide, you get the remainder in.
Like when we divide, the remainder we are going to get, that variable that we use to divide is not going to be in that remainder.
So just like same thing like when we are partially evaluating.
Exactly.
Just describe it from when we have the polynomial in like n minus one variable system.
Yeah.
So the quotient we get before we do the next division, what happens to it?
The quotients, you know, our quotients are always our proofs. So every factor is going to have a corresponding proof. So that's just what this means. Every factor with its corresponding proof. But then we are going to sum everything together. Does it make sense? Sure. Can we do an example? Okay. So, which polynomial should we use?
This is the initial one.
Is it two variables, okay, or should we make it three?
Don't make it three. Give your value or polynomial.
We can make it three, right?
Yeah.
Okay.
You know your polynomial. There's three values.
Okay.
3AB plus 4C.
3ab plus 4c. Okay. This polynomial, we want to basically generate proofs for it, right? So first of all, we're supposed to commit to the polynomial, and then after committing to the polynomial, the verifier will send the points the verifier wants to open the polynomial at, and then the prover is going to evaluate the polynomial at those points and send the corresponding proof to the verifier. So this is what we are going to do now, right? Okay, so first of all, we need a short-set setup, right, in order to get the, for now we're just going to work in the coefficient form, right, so that everybody understands. Yes, so that everybody understands what is going on, right? before we'll now look into the evaluation form. Hope that's okay.
Yeah.
Okay. So okay, so before we continue, what what have we learned today? Yes. What have we learned today? What have you yes. What have you picked? Like multilinear KZG is the umbrella term. Like what exactly? Like have you learned anything new today? Have you learned any new concepts?
Yeah.
What?
How to get powers of power from
Okay. No, no, no.
If you multiply the this it don't work.
No, see, actually, like, I think it's just skill issue, right?
Yeah.
It's skill issue, actually.
I don't think
So I think, like, you guys can actually look into it. On my own end, I'll try to look into it.
you know,
So,
okay, you know why I
Okay.
think it's not skill.
okay.
We did more, we have been more personal. We have series. So there's a way to, in that series, to generate your current sequences. When you are doing PD, why you look like that? When you are doing PD for like series solution for PD, you know the so the point is that sometimes when you want to generalize, like you don't have to expand. When you expand, you won't get the whatever you want to get. If you now do it that way, you will completely miss it. So you get it.
Yeah.
So it relates to that for this one, if you expand,
If you expand, you will not always get 50.
No, see, that expansion, I feel is,
They are linearly independent.
How do you get it?
I think that is actually, like, the problem is how we're actually looking at that stuff. Still trying to figure out because the idea is when you evaluate it at A and you evaluate it at B and you evaluate it at C, that's when you're going to get V, right? So, but I'm thinking, I'm not very sure, something I need to verify, that when we actually do the division, when we actually do the multiplication, true, we're no more saying A and B and C. But basically, it's basically another statement. Maybe A or B or C, right? But I need to verify that.
Yeah, probably it's not commutative.
Huh?
Probably it's not commutative.
The division or the multiplication.
Yeah, that might be it.
But it should, right?
Because
Technically,
if you evaluate the polymer at A, B, C, like A, B, C, will it be the same if you evaluate it at B, A, C? Will it be the same if you
okay, no.
evaluate it at
Okay, that's what you're
C?
driving
I'm
at.
trying to say that
Oh.
probably that evaluation over polynomial is not commutative. Like, because we're looking at, I know we're just looking at it like A, B, C, but then
Oh, that multiplication since can be a permutation.
yes, exactly.
I think that's a good way to think about it, but I can't say.
Yeah.
But that sounds right. That sounds right. I think it's just we just need to look into it to make sense. Okay, so you guys were telling me what you've learned, right? So what else?
Learn how to evaluate the polynomial as an evaluation form to get the
You
yeah.
just product between polynomial and
on the Lagrange basis.
How to evaluate a multilinear polynomial at tau?
Okay,
That is
at
just
tau for all the
all the
variables.
integers there.
For the multilinear, don't worry, I think we are going to do it. This example we want to do, we will do it. So, is everybody, are we together? Sure? Sure? Why is it fast looking scant? Eh? A break?
Oh.
What is it time?
Which one we go?
Okay, actually, let's take a break. So we'll be coming back by 1:30. Okay? 1:30 is fine, right?
Yes.
1:30 I'll be starting. Whether the class is empty. Yeah, this example that we're going to do, we're going to do everything like from the commitment to everything.